Last week we talked about supervised machine learning. Where the general idea is that we had a bunch of training data with known features and known classifications that we represented as a vector of x are the features, y is the classification. And we put all of this training data into some sort of algorithm. And we got out a rule for classifying new unknown points. So we had a rule for classifying points that had known features x, but unknown classification. And so we saw two examples of this type of algorithm last week. We saw k-nearest neighbors and identification trees. And today we're going to add neural nets onto that list. So we'll start with looking at a single neuron to see how we can compute things with a neuron to classify points. So let's say that we have 3 inputs that we'll call x1, x2, and x3. Each of these inputs will go along a wire and be multiplied by a weight. So we'll have weight 1, 2, 3. And then these will all go into a summation box and get added together. And that sum will go into a thresholding function, which has some threshold t. And in the end, we'll get some output, which will be either a 0 or a 1. So we have a binary output. So basically what we're doing is these are our features, and we're given the feature values that are numeric, and then we're going to get out a binary classification, one of 2 classes. So as an example, let's say that we have x1 is equal to 1, x2 is, say, 3, and x3 is negative 1. And then let's say we have weights 2, 2, and negative 1. Then what we're going to do is we'll multiply each input by the weight and get some value out on this wire. So what would we get out on the top wire? 2, because we multiply the input 1 times the weight 2. Then the next one, 6. And then we'll get positive 1. So then we'll add these numbers together in our summation box. So what would come out of the summation box? 9, because we're adding 2 plus 6 plus 1. So we get 9 out there. And let's say that our threshold is some value 12. The way that we're going to deal with the threshold, in this case it's a stairstep function. So the stairstep function looks like this. It has some threshold t and it takes in a value that we'll call x. And then that will be, it'll output either 1 or 0. 1 if x is greater than or equal to t, and 0 otherwise, so if x is less than t. So if we graph that, it'll look like this, where it's 0 for a while, and then it goes up steeply at the threshold, and then it has a value of 1. So it's ranging from 0 to 1. This is x, and that's the threshold t. So now if our value x is 9 and our threshold is 12, will this output a 0 or a 1? 0. Because the question that we're asking here is 9 greater than or equal to 12? And the answer is no, and 0 represents false or no. So that's how we can do forward propagation through a single neuron. You could imagine chaining a bunch of these things together where we take this output and put it into the next neuron. But in order to represent that more concisely, we're going to encapsulate these two things into a single symbol so that we don't have to keep drawing out the summation and the thresholding. So we're going to take these, and we're going to say that those will be represented by a single symbol, which is a circle with a stair-step symbol in it. So now neural net is equivalent to one where we have our 3 inputs with their weights going into this function, this symbol, and our output coming out, and it still has some threshold t. So this is just a simpler way of drawing it. It does the exact same thing. So now you could imagine chaining a bunch of these things together where we might have, for example, say our 3 inputs. You can have any number of inputs. And they might all go into some neuron, and some of them might go into another neuron. And then those might go into some additional neurons. Right now I'm just wiring this arbitrarily, so don't worry about copying it exactly. And then those might go into more neurons. And then in the end, we'll get a single output neuron that will give us a 0 or a 1. So this neural net will do a whole bunch of computation, and we'll get a single value out at the end. And so you can imagine following the numbers through where each of these guys is going to output a 0 or a 1. Or we might have something like this, where all of the numbers go through, and depending on the thresholds and the weights, we'll get out a 0 or 1 at the end. So that's called forward propagation, because we're just going forward through the neural net. So we're going from the inputs to the outputs and getting a 0 or 1 out at the end. So now let's see, well, another thing we can do is label the parts of this neural net. So we have this first layer of neurons is called the input layer, and we'll see in a few minutes why that layer is special. This final neuron is in the output layer, or final layer. And in our case, that will always only be one neuron because we were just having a single output. And then everything in between are the hidden layers. So in this case, we have 2 hidden layers. In some cases, we might have less or no hidden layers. In a deep neural net, you might have like 10 hidden layers. But that's the general idea of how a neural net is structured. So now let's see what we can do with a single neuron. Let's say that our inputs, we have 2 inputs, x and y, with weights a and b. And those go into a neuron with some threshold t. So this output will be either 1 or 0. And let's see what would cause it to be a 1 or a 0. So if we're propagating the x forward along this wire, what would we get coming out of the A weight box? AX, because we multiply the weight times the input x, so we get AX there. And then on the bottom, we would get BY. And then we're going to compare it to the threshold t. So what we're asking here is AX plus BY greater than or equal to t? And if the answer is yes, then we'll get a 1 out. And if the answer is no, we'll get a 0 out. So we could say that the output is 1 if AX plus BY is greater than or equal to t, and 0 otherwise if AX plus BY is less than t. So now this is the equation of a line in Cartesian coordinates. So we could try graphing it in a plane. So we could have x and y, and this might be some line like, say, like that. How would we represent, this would be a line ax plus by is equal to t. How would we represent the greater than sign? Yeah, shade one side of the line. So if all of these parameters are positive, we would be shading above the line. So now this is sort of like, this is reminiscent of k-nearest neighbors, where we drew lines in the space to represent decision boundaries, where on one side of the line you're classified as a 1, and on the other side you're classified as a 0. So now this is how we can use a single neuron to classify some training data by putting a line in and shading one side of it. So let's look at a specific example. Let's say that we want it to compute a Boolean AND function. So we have two inputs, x and y, and they can each be 0 or 1. And then we want to compute the AND of x and y. So 0 means false, 1 means true, and then AND is true only if both x and y are true. So what would the AND column look like? Yeah, only the last one is a 1, and those are all zeros. So now we could graph this where we have x and y. And what we're going to do is we'll draw a circle at each point to represent the 4 points, the 4 combinations of x and y. And then we're going to shade in the points that have a value of 1. This is a notational thing. So we'll shade in that point and leave the others unshaded. And so now the question is, how can we use a single neuron to classify that data so that the 1, 1 point is classified as a 1 and the other 3 points are classified as zeros? Yeah, we can just draw a line there. So there are many possible lines we could draw. Like we could have one that's almost vertical or almost horizontal. There isn't really a right or wrong answer here, but we're going to do this one that crosses at 1.5 just because it leaves a nice margin of error. So that crosses both axes at 1.5. What would be the equation of that line? Yeah, y is negative x plus 1.5. So now what we want to do is just rearrange this equation so that it looks like one of these things. So first we have to decide which side of that line should we shade. Yeah, we want to shade this side where the shaded point is. So would that be y is greater than or y is less than? Greater than. And if you're not sure, you could always plug in a point. An easy one is you could plug in 0, 0, and we would see, is 0 greater than or equal to 0 plus 1.5? The answer is no, so that's correct. It gets classified as a 0. So now we just need to rearrange this equation to look like ax plus by is greater than or equal to t. So we can move the x to the other side, and we get x plus y is greater than or equal to 1.5, which is the same as 1x plus 1y is greater than or equal to 1.5. So now we can draw a single neuron neural net like this. Yeah?
Wait, where did you get that equation from?
Get this equation? Yeah. So this is just the equation of the line.
Right, but how did you choose?
How do we choose the line? Yeah. It was arbitrary. Okay. So you could also choose a line that has a much steeper slope and crosses like right here or something.
Just as long as it separates.
Yeah, as long as it separates the data. And so when we get to actually training the neural net will decide that for itself, and as long as the data is classified correctly, it won't care. But yeah, it was an arbitrary line. And you could also multiply through the whole thing by like 20 or something and get 20x plus 20y is greater than or equal to some value. Okay, so now we want to make a single neuron neural net that classifies this data. So we're just going to map this equation onto a neural net, where we have our inputs x and y, some weights going into a neuron with some threshold, and we'll get an output. So what would be the weight for x? 1, because that's just 1 times x. And then similarly for y, and what would be the threshold? 1.5. So we can just read that off the equation. So you could do a similar thing for other logic functions. Like if we did OR, then we would have these 2 points also shaded, and the line would just move down a little bit. Let's try not function. So a not function is only going to take in one of the inputs, but we still have 2 inputs. So we'll compute the not of x. what will that column look like?
1, 1, 0, 0.
Yeah, 1, 1, 0, 0. So it's just the opposite of the x column. Then we can graph that. So we're going to shade in all of the points when x is 0 and not shade the ones when x is 1. So we'll get those two shaded. And then what can we do to separate this data? Yeah, we can just have a vertical line. Again, it could cross at any point between 0 and 1, but let's just say it crosses at 0.5. Do we want x less than or x greater than? Less than in this case. So that means we're shading the left side of this line. How can we convert this into an equation with a greater than sign? Yeah, just multiply through by -1. So then we get -1x is greater than or equal to -0.5, and we could add in a 0y because that won't affect anything. And then we could map that onto a neural net just like we did with AND. So what would be the weights for x and y? Yeah, so just reading those off the equation, and then the threshold is -0.5. So you get the idea. Basically, we're drawing a line, figuring out the equation, and then putting the parameters onto the neural net. Let's try one more of these that might be a little more complicated. Let's try XOR. So XOR will be true whenever either x is true or y is true, but not both. So what will that column look like? 0, 1, 1, 0. So we'll graph that. And we'll have 0, 1 shaded and 1, 0 shaded. Can we draw a single line to separate that data? No, so now we're going to have to figure out how to combine multiple line shadings. So if we go back to this neural net that we drew symbolically, let's see what happens if we add a second neuron to it. So we'll call this threshold T1. And then we'll draw a second neuron down here. And we'll again have x and y going into it. And this time we'll give it weights C and D and a threshold T2. So now we can say that this one is computing the equation ax plus by is greater than or equal to T1. And the lower neuron is computing ax plus by, cx plus dy. Cx plus dy is greater than or equal to some threshold T2. So if we draw both of these lines on the same graph, then we might have something like this line shading one side of it, and that line where we're shading one side of it. And so now what we can do is combine these shadings using some sort of logic function, because what's happening here is each of these outputs will be a 0 or 1. And we just figured out how to do something like combining Boolean inputs using an AND function. So here we just have these Boolean values. So we could connect them together using some sort of logic function here. So this thing will be a logic function. If we used an AND function, how many of the regions in the space would get shaded? So if we have this region, those two, and the lower one. Just one. So if we did an AND function, we would get this region shaded. What if we did an OR? Yeah, we would also get the ones on the sides. So that would look like this. That's an OR. So now we can go back to our XOR that we're trying to make and draw two lines and combine their shading. So what two lines might we want to draw? Two parallel lines? Yeah, there are a few different ways we could do this, but let's try that line and that line. So this line will be AX plus BY is greater than or equal to, oops, those are not numbers. If this crosses at 0.5, this would be 1x plus 1y is greater than or equal to 0.5. Well, which side of this line do we want to shade? Do we want to shade above it or below it? Above it, yeah. So that will be greater than 0.5. Which side of this line do we want to shade? Below. So that means that this green line will be 1x plus 1y is greater than or equal, is less than or equal to 1.5, and we can reverse that sign by negating everything. So we have negative 1x minus 1y is greater than or equal to negative 1.5. And then what function do we want to use to combine those shadings? And. So now we can just map that all onto this neural net, where the purple line can be A, B, and T1. So we have, that's 1, 1, and 0.5. And then the green line will have weights negative 1, and negative 1.5. And then we said we want an AND function over here. So what will be the weights for our AND function? Do we know that? So that's just going to be what we did over here. We can copy it directly, and we have 1, 1, and 1.5.
You know the 1.5 is still going to work?
Yeah, so this AND function is the AND of Boolean inputs, because these are just zeros and ones. So this is the same thing as, there are only 4 cases. So any line that would correctly compute AND there would work the same here. So we could test whether this neural net is working correctly by plugging in some input point. So we could try something like plugging in 0, 0. So we'll have x is 0 and y is 0. When we multiply them by their inputs, those will all be zeros. So what would we get coming out of this top neuron if we're comparing 0 to 0.5? 0, because 0 is not greater than 0.5. But then here we would get a 1, because 0 is greater than negative 1.5. So we would multiply those by these weights and get 0 and 1. And what would we get out in the end? 0. And so that's correct, because we were looking at this point and it's supposed to be a 0. And you could do the same thing to check the other points, and you would see that you would get 0 or 1 as you expect. So that's the general idea of drawing pictures with neural nets, graphing the output, and being able to classify points. So we could add to this picture that the input layer has a specific function, which is to draw lines in the space. So the input layer draws lines. And specifically, it's going to draw one line for each neuron. So here we had 2 neurons, so we drew 2 lines. So 1 line per neuron. And then all of these remaining layers are going to compute some sort of logic function. Specifically, they're going to combine line shadings using a logic function. Okay, are there any questions on all of this? Okay, next we're going to look at backpropagation, which is a way of automatically determining these weights and thresholds so that we don't have to manually figure them out. Because so far what we've been doing is just examining the data and finding a line that looks good to us as humans. But that's not practical if you have a much larger training data set. So backpropagation. So one way of thinking of a neural net is it's approximating a function, because the idea is we have all of these inputs that are going into some sort of thing, which is this neural net. And then there's some desired output that we want to get out on the other side when we're training it. So this is out star is our desired output. And the idea is if we tell the neural net what the inputs are and what we want the output to be, it should be able to adjust its parameters so that it correctly computes that output. So this is, you could think of this as some sort of black box function, but what's going on inside that is there are a bunch of weights and thresholds floating around in this cloud. And so these are all the parameters that we can adjust to make the neural net correctly compute some function. So one thing we want to do first is simplify this so that instead of having to deal with both weights and thresholds, we can just have weights. So that's where the threshold trick comes in, which we saw in lecture. So the idea is, if we go back to our basic one neuron neural net, we said it was computing ax plus by is greater than or equal to t. But we want that threshold t to be 0 instead of t so that we don't have to deal with thresholds. So we said this does ax plus by is greater than or equal to t. But if we move the t to the other side of the equation, we can get an equivalent equation. Ax plus by plus t times -1 is greater than or equal to 0. So all we've done is move the t to the other side. And then this would be a neural net with 3 inputs. So we still have x and y with weights a and b. But now we have this constant input -1 with a weight of t. So now what would be the new threshold for this neuron? 0, because it's just this 0. So now this is convenient because we still have the same number of parameters to train, but all of the parameters can be treated as weights. So instead of having to worry about whether it's a weight or a threshold, we'll just say that all of them are weights. And now we just have to find a way to adjust the weights. Let's see. So now another problem we have to deal with, in lecture we saw that there was some issue with using the stairstep function. What was that issue? So we're going to be doing gradient ascent, which requires taking derivatives. Can you take the derivative of a stairstep function? No, so it's not differentiable at these corners. So we're going to approximate it using a sigmoid function. The sigmoid will be very similar, but it has 2 parameters, the steepness and the midpoint. And this is on the handout, so you don't have to copy everything down. So S is steepness, and M is midpoint. And it'll take in some value that we'll call X. And then it'll have some equation. So the way the sigmoid looks is it's basically a curvy version of our stairstep function. So it'll do something like this, where it still goes between 0 and 1. But now instead of a threshold value, up here we had our threshold t, it's going to have some midpoint m, which is its inflection point where it has a value of exactly 0.5. And then it'll have the steepness parameter, which determines how sharply it goes up. So another sigmoid could look something like this, which is steeper. And so that's just that's just determined by the steepness S. So the general form of the sigmoid equation is 1 over 1 plus e to the negative steepness times x minus the midpoint. And so a simple example of a sigmoid is 1 over 1 plus e to the negative x. So just generally this shape of function. So then one more thing we need is a way to judge the performance of the neural net, or how well we're doing with training it. Because we know that we want it to produce the desired output, but we need some way of judging whether it's getting closer or further from the desired output. So that will be the performance or accuracy function. So the performance is the same as the accuracy. The accuracy function will take in the desired output and our current output. So the desired output will be either a 0 or a 1, depending on the desired classification. And our actual output will be, if we're using a sigmoid function, some value between 0 to 1. And that's going to be equal to negative 1/2 times the desired output minus the actual output squared. So this function will just look like an upside down parabola. So it might be something like this. This is the output. And so when the output is equal to the desired output, that's this point right here. So the maximum value of the accuracy is 0, so it always is either negative or 0, and the goal is to get as close as possible to that point on the curve. So now there's this concept of gradient ascent. We can think of the output of our neural net as some function of all of the weights. Because as the weights are the only things that can change, and as you vary the weights, then that affects what the output will be. So that's what we're doing here, where we're graphing the output and seeing how the accuracy changes. But we can also look at those weights one at a time. So if we just look at the accuracy with respect to one of the weights, say weight 1, then the accuracy might go up and down as we change the weight depending on everything else that's happening in the neural net. So we might end up with some weird function like this sort of thing. And so this is how the accuracy changes if you just vary that one weight. And then you can think about, let's say that currently the weight has a value right there. If we look at the slope of this curve, you can tell whether we should be increasing or decreasing the weight to get better accuracy. So if we look at that slope there, if we want to increase the accuracy, should we increase weight 1 or decrease it? Increase it, yeah. Because if we increase it, then we might move it a little bit to right there, and then we'll be higher up on this accuracy curve, and that's higher accuracy, which is better. There's a parameter R, which is the rate constant, or step size. And that determines how big of a step we take. So there are trade-offs here. If you take really small steps, it'll take forever for you to get to the local maximum, and you won't ever be able to get off the local maximum. Whereas if you take a really big step, then you might completely jump over it and end up somewhere worse. So in general, the rate constant will be given to you, so you don't have to worry about that. But those are some of the considerations if you were choosing a rate constant. So what backward propagation is doing is it's not just looking at one weight at once, it's looking at all of the weights at the same time. So it's hard to draw a picture in more than 3 dimensions, but if we had just 2 weights, then we could graph the accuracy with respect to those 2 weights, and we might have some sort of surface like this. And if we're at some point on the surface, like say right here, then we can look at the gradient of the surface and figure out oh, we should adjust the weight so that we go that way to go up this hill. So we're basically just hill climbing, and that would tell us how much we should adjust weight 1 and how much we should adjust weight 2. So you could do the calculus to figure this out, and you could do the chain rule over and over, but instead we're going to use a bunch of quick formulas that are on the handout, so you don't have to worry about the calculus and slopes and gradients. So the formulas on the handout will help us to update a particular weight in the neural net, because the general idea of backpropagation is we're trying to update each of these weights. So if we have, say, some weight here which is going from a neuron A to a neuron B, then here's the neuron A, and here's the neuron B. And let's say that we want to update that weight in backpropagation. Then we want to compute the new value of that weight, which will just be equal to the old value plus the change in the weight. So here's the old value of the weight plus the change in the weight. And then the change in the weight will be equal to the rate constant r times the output of neuron A, so that's going to be whatever value is on this wire, times some value that we'll call delta B, which is the property of neuron B. So this value delta B will depend on whether the neuron B is in the final layer or not. So if the output comes out of neuron B, is it in the final layer? Yeah, because that's the definition of being in the final layer. So in that case, we're going to have delta B will be equal to the output of neuron B, which is just equal to the overall output, times 1 minus the output of neuron B, times the desired output minus the actual output. And so that's if B is in the final layer. And then otherwise, if B is not in the final layer, then we might have a case like this. If it's not in the final layer, then there will be one or more neurons coming out of it. So let's say that we have 3 neurons coming out of it, and then the neural net might continue on after that. We'll call those C1, C2, and C3. And then each of those will have some weight. So like this would be the weight going from B to C1. And so what we'll do is the formula still starts with the output of B times 1 minus the output of B. But then we're going to sum over all of these outgoing neurons. So say it's times the sum over the outgoing neurons C sub I. And for each of those neurons, we'll take the, what is this? The weight going from B to C sub I, so that's like this weight, times the delta value for this neuron C sub I. And so that's if B is not in the final layer. Okay, so we're going to do a quick example with these formulas so they'll all make more sense. So in this particular example, someone named John Connor has built a neural net. And he's trying to distinguish between human-shaped Terminator robots and real humans based on 3 input features. The features are whether they misuse colloquial expressions, whether they have super strength, and whether they're good with guns. And then there's some neural net that has 3 neurons. And then there are weights on the wires that will number 1 through 6. We'll label these neurons P, Q, and say U. And then we're given a training point. So this training point is a human named River from Firefly. And she misuses colloquial expressions. She doesn't have super strength, but she is good with guns. And we're told that 0 means human, so our desired output, out star, is equal to 0. So we want River to be classified as a 0 with this neural net. And so we do forward propagation. And let's say that when we do forward propagation, we get our current output is some value z. And now the question is, how do we what would be the updated value of weight 1 if we were doing backpropagation using this training point? So what would we do first to calculate the updated weight for weight 1? What do the formulas say? Yeah, we need to figure out whether it's the final layer, but we can start at the very top. So we want the new weight for weight 1. So we can say W1 new will just be the old weight plus the change in the weight. And then we need to know the change in the weight. In this case, we're given some rate constant. Let's say that we're told R is equal to 10. Then we would have 10 as our rate constant. What's the output of A in this case? What is A? One. So in this case, A is not actually a neuron, it's an input. A is this input M. So the output of M is just the value of M, which is 1. So that will be times 1. And then we have delta B. What is B in this case? Which neuron is it? Yeah, so we have the weight going from M to P in this case instead of A to B. So delta B will be delta P. So now that's the neuron where we want to figure out whether or not it's in the final layer. So is neuron P in the final layer? No, because there's a neuron coming out of it. So we'll use the second delta B formula. And we'll get delta P is equal to, what is the output of P isn't given. Let's just say that it's some value out P equals, I don't know, let's say it's equal to some value N. Then we'll have N times 1 minus N. What neurons are we summing over for our outgoing P sub I? Just U, because that's the only outgoing neuron. So we're just going to sum over U, and for U we're going to take the weight going from P to U. So what is that weight? W5. And then we want the delta value for neuron U. Is U in the final layer? Yeah, it is. So then we can use the first formula. So what is the output of U? Z. We're given that here. So we have Z times 1 minus Z times, what's the desired output? 0. 0 minus the actual output is Z. And so then to figure out this updated weight, we could just plug delta U into that equation, delta P into there, delta W into there, and then we can get this new value of weight 1. And so if you ask where did these N's and Z's and all the values come from, that would be from doing forward propagation at the beginning. If we had done forward propagation, we would get some sort of numbers or expressions for N and Z. Are there any questions on this? Okay, so that's how backward propagation works to train the neural net, and you can use forward propagation to classify points with the neural net. And that is how neural nets are a supervised machine learning method.